This is an alien world. There is no light except that made by bizarre creatures that live here. There is no sound but the bubbling of hot, sulphurous vents. It's a world that very few humans have ever set eyes on. And yet, this is a part of our world. We know less about the deep oceans of planet Earth than we do about outer space. The oceans are deep, dark, and full of mystery. Most of what we do know about them was only revealed in the last 60 years, when technology was finally able to see through the immense expanses of water. We now know that the oceans sit on top of oceanic crust, just as the familiar continents are fixed to continental crust. In the 1950s, a group of scientists became interested in the oceanic crust, and in particular, its magnetic properties. What they discovered changed how we understood not just the oceans, but the entire history of the Earth. Consider a sailor's compass. The idea behind a compass is that it will always point northward, allowing the user to navigate across a featureless ocean. It is influenced by the magnetic field generated in the Earth's core. Sailors have used compasses for many centuries. However, a compass can be influenced by forces other than the Earth's magnetic field. In the late 18th century, sailors from Iceland noticed local disturbances in the magnetic field that caused navigational errors. The disturbances were put down to magnetized rocks on the seabed around Iceland. In World War II, a new instrument was developed that could be placed on an airplane and used to detect submarines in the Atlantic Ocean. This device was a special kind of magnetometer, an instrument for measuring magnetic anomalies. After the war, it was modified and used to identify those disturbances the sailors had encountered. Planes flew back and forth across the Atlantic with magnetometers on board, creating a magnetic map of the seabed. Scientists knew that the rocks making up the oceanic crust were mostly volcanic, and they contained magnetite and other magnetic minerals. However, the scientists didn't expect them to form any particular pattern. Magnetic anomalies would be randomly distributed across the seabed, or so they thought. When the first magnetic surveys were finished, scientists were absolutely blown away. They did not expect what they actually saw: stripes of magnetic anomalies that switched between positive and negative. They saw a positive stripe next to a negative one, next to another positive one, and so on. What caused this pattern of magnetic stripes? It turns out that the Earth's magnetic field is not entirely static. It moves over time, which causes the north and south poles to drift slowly. Every few million years, it even flips around, so north and south are completely switched. When the rocks in the oceanic crust are formed, they preserve the direction of the magnetic field at that time. If it matches the direction of today's magnetic field, it can be measured as a positive anomaly. If the direction of the magnetic field is opposite, it can be measured as a negative anomaly. However, even this revelation doesn't explain the stripes on the seabed. To form stripes of alternating positive and negative anomalies, different parts of the seabed would have had to form at different times. In fact, the whole seabed would have had to have moved over time. In the Atlantic Ocean, the magnetic stripes are symmetrical on either side of the mid-Atlantic ridge. Rocks on either side of the ridge have preserved the imprint of the current magnetic field and are geologically the youngest rocks in the Atlantic. As we look further away from the ridge, we observe the well-developed magnetic stripes. We can also see that the rocks get geologically older toward the eastern and western edges of the ocean. This model demonstrates how the seabed itself must have moved over time. The two strips of paper represent sections of oceanic crust that emerge from a mid-ocean ridge in the centre. As molten rock is erupted at the mid-ocean ridge, it cools and solidifies, preserving the orientation of the Earth's magnetic field. Then the orientation changes, the magnetic field flips, and this change is recorded in the younger rocks. As more and more rocks are added in the centre, the oceanic crust spreads further and further out. The magnetic stripes develop as the magnetic field keeps flipping back and forth. In the Atlantic Ocean, this whole process took 200 million years. It was very, very slow going. In order to produce the pattern of magnetic stripes that was discovered in the 1950s, the seafloor had to spread out. The Atlantic Ocean actually grew over 200 million years, and the continents on either side had to separate from each other. It sounds crazy, but this is the only reasonable explanation for how the magnetic stripes were formed. Actually, that sounds a lot like Wegener's idea of continental drift, except it was given a new name: plate tectonics. Magnetic striping was a key piece of evidence in proving Wegener's ideas correct. Unfortunately, he didn't live long enough to experience the satisfaction of being right. Not only did the discovery give sailors the data they needed to correct their compass measurements, it also paved the way for a bold new scientific theory. Plate tectonics underpins our entire modern understanding of how the Earth works. It explains how volcanoes and earthquakes occur, how continents shift over time, and how the planet itself has developed. Time is as deep as the ocean, and there is plenty of it still to explore. I hope you found this video helpful and you're keen to learn more. Thank you very much for watching.